Alright, so here is our first example. We're going to get two of these. So I kept the Taylor series definition there and the Maclaurin series up on the screen to get into this one. Find the Taylor or Maclaurin series. We're going to do this for f of x equals the natural log of x squared plus 1, and c will equal 0. And so we can tell, because we're centering at 0, this will in fact be a Maclaurin series. Try to zoom in a little bit here. Make things a little bit bigger, a little bit less fuzzy on the video. Okay, so let's dive in to the example. What are we going to do? So remember that for any f of x, really when you represent it with the Taylor-Maclaurin series, what's important is that coefficient. We know we like to start at 0, right? We know it's going to be x minus c to the n. We even know in the coefficient it's going to be over n factorial. That's never going to change. So what really differs from function to function is the numerator of that coefficient. The derivative of your original function evaluated at c. So here we've got the natural log of x squared plus 1. So we're going to need to take several derivatives, okay? And we're going to need to evaluate them all at our c. And then we'll end up with several terms there. And we'll see what we can do with that. So the way we're going to begin is by taking several derivatives and plugging in c. So here we go. See if I can get all this on the screen. I kind of made this big table, and I recommend you do something similar. So I've got my original function here, like the 0th derivative. So if I evaluate that at 0, well, then I'd have the natural log of 1, which also equals 0. Okay. Then we're going to go on. We're going to look at the first derivative. Okay. So here our first derivative, we got a chain rule going on, right? 2x over x squared plus 1. And if we evaluate that at 0, f prime of 0, well, that's going to equal 0 as well. Okay. All the zeros happening so far. Let's look at the second derivative. Now we need quotient rule. Well, you know, I'm not going to talk through the quotient rule. There it is, if you want to look at it closely. When you simplify 2 minus 2x squared over x squared plus 1 quantity squared, and we need to evaluate this at 0. And finally, what we get 2 over 1, we get a non-zero result. Okay, let's keep going now. Probably at some point you're going to be asking, how many derivatives do we really need? Here's a good rule of thumb, and probably the way I will specify on tests. You want at least 3 non-zero results after you plug in your C value. 3 non-zeros. So we keep getting these zeros here, right? I mean, up to this point, we've gone this far. So we had 0, 0, 2, 3 non-zero results. Some cases you may very well want more. That'll make more sense as we go through the rest of the problem. Okay, so the third derivative, I'm not going to show you the details of obtaining that derivative. Obviously, we would need quotient rule again. I don't want to encumber us with details of derivatives here, although that would take a little bit of time, right? You would end up with 4x to the third minus 12x over x squared plus 1 to the third after you simplify. Okay. So if I evaluate that at 0, oh man, 0 over 1, that's going to be 0 as well. So we definitely need to keep going. Fourth derivative, again, I'm not going to show you all the details. We don't need all that for our discussion here. Negative 12x to the fourth plus 72x squared minus 12 all over x squared plus 1 to the fourth plug 0 into that, and we end up with negative 12 over 1, negative 12. That's only our second non-zero entry. So let's keep going. Oh man, okay, so another big quotient rule. The fifth derivative, you can barely see that little 5 right there. The fifth derivative, 48x to the fifth minus 480x to the third plus 240x. Let me pull this up a little bit higher. All over x squared plus 1 to the fifth. So plugging in 0, everything in the numerator is 0. So there's another 0. We need a sixth derivative, and turns out this will do it for us. Another big quotient rule, negative 1200x to the sixth plus 3600x to the fourth minus 3600x squared plus 240 over x squared plus 1 to the sixth. When you simplify that, plugging in 0 now, we get 240 over 1. And now we have 3 non-zero derivatives evaluated at C. Okay. What are we going to do with all this information? All right, well, it was these numbers that we were after, right? Okay. I'm actually going to use all of them, including the zeros, but you'll see why the non-zeros are really the only helpful parts. So I'm going to go to the next page here. And what I'm going to do is just start off by writing out that Taylor series formula again for us. Okay, so if you recall, we found f of 0 was 0, f prime 0 is 0, f double prime 0 was 2, f triple prime 0 was 0, fourth derivative at 0 was negative 12, fifth derivative was 0, sixth derivative was 240, if I remember correctly. Let me just flip back. Okay, yeah. Okay, so using these numbers, here's what we can do right here. Boom. And hopefully that all fits just about on the screen if I pull it camera back a little bit. So at n equals 0, right, I'd have the 0th derivative evaluated at 0. That's right here, and it equals 0. So my 0th term, I've got 0 over, and then I fill in the ends. 0 factorial, I'm centering at 0, so that's x minus 0 to the 0 power. So a lot of zeros going on, but this 0 is right there in the numerator. Then we've got over 0 factorial, x raised to the 0, those are the values of n. Okay, the second term, my numerator is right here. That 0 is my numerator, and then n equals 1, so 1 factorial x to the first. Okay, finally we make it to n equals 2, so that's the second derivative at 0, which happened to be 2, and then n equals 2, so 2 factorial and x squared. N equals 3. Well, the numerator is right here, that's 0. 3 factorial x to the third. N equals 4. Negative 12, so you notice I put minus 12. 4 factorial x to the fourth. N equals 5. Numerator is right here, the 0. 5 factorial x to the fifth. N equals 6. 240. 6 factorial x to the sixth. Okay. Let that soak in. All we're doing is following our series, expanding it, and filling in those numerators as we go. So certainly anything with a 0 numerator, which there are quite a few here, just disappear. Okay, and we can write it just with the non-zero numerators. The terms with non-zero numerators. So we've got 2 over 2 factorial x squared minus 12 over 4 factorial x to the 4th plus 240 over 6 factorial x to the 6th. And now you notice something. I actually put a minus here. Previously I had a plus. I know it's kind of fuzzy because I'm looking at these in positive, negative, positive, and I'm gonna be pretty confident that that next one's gonna be a negative. If I wanted to be absolutely sure, I could find more derivatives and plug in 0 and just see what happens. Okay, let's simplify each of these fractions. And you notice I even circled this part. Well, 2 over 2 factorial, this is 1. 12 over 4 factorial. 4 factorial is 24. Right? That's 1/2. 6 factorial. I don't remember what 6 factorial is, but apparently that whole thing reduces to 1/3. 6 factorial is 720. So 240 over 720 is 1/3, yeah. So definitely get at least 3 non-zero because here, I mean, you don't want like one term here like that. It's like, I don't even see the pattern, you know. Okay, so you notice I circled this one. In some questions, I'm going to ask you, like on a test, let's say, I'm going to ask you, hey, just get the first like 3 non-zero terms of, here it's the Maclaurin series. Other times though, I will ask you to put it in the series form with the sigma. Okay, so this might well be an answer if I said, hey, you know, just find the first 3 non-zero terms of the Maclaurin series. And then we kind of like the ... indicating there's more than that, but there's the first 3 non-zero terms. But what if I asked you to go a step further and represent this, you know, in the way we would prefer with the summation? Then you're going to have to look at your terms and notice the pattern that's going on there, right? So to represent it in the power series form, let's take a look. Well, there's some patterns here that are actually pretty reasonable we could do. You notice the powers of x are just the even numbers, 2, 4, 6. If we really wanted to confirm that the next one was x to the 8th, we could find more derivatives and go about that, but it is true here. We also notice the positive, negative aspect. Okay, so it's an alternating power series. And notice those coefficients, right? 1, 1/2, 1/3. So you can get something from there. It'd be a lot more interesting if we were in class together and we could really talk through, each of those aspects and how to represent them. We're not, so I'm just going to show you everything. It's a lot more fun to kind of have like experiment and guess and check your way, but that's not what we've got here. So what I've done is I've represented this power series in 2 different ways. The first starts at n equals 0, which, all things being equal, we would prefer it to start at 0, but it may be more natural here to start at 1. Let me raise this up so it's not quite so fuzzy. Let's look at both. Maybe let's even start at n equals 1, because I think certain aspects are more natural. You think, okay, so what's happening with the powers of x? They're the evens. Well, if we start at n equals 1, that's just x raised to the 2 times n. X squared, x to the 4th, x to the 6th. Very nice. Also, what you're dividing by, oh, that's not n factorial, my mistake. It's just n. Right? 1 over 1, 1 over 2, 1 over 3. Boom. Now it is alternating though, and if you start at 1, you just want to make sure that your first term is positive, then the second term is negative, and so on. So to make sure that your first term is positive here with the alternating, we'll need it to be n plus 1, so it ends up getting raised to the second power for our first term. And there you go. Now if you wanted to think of it as starting at 0, a little adjustment here. Let's see what we did. I think I added 1 to some of the n's. So instead of x to the 2n, it's now got to be 2 times n plus 1, because we want it to begin, plugging in 0. We still want to start at 2. Okay. Also, this denominator, it's like we need to go 1 higher. So instead of starting at n, it needs to be n plus 1. So when I plug in 0, I still get 1. But now for the positive, negative, positive, if I want it to start at positive, I can leave it as n because that would raise it to the 0 power. And so that would work. So here's the non-series form where it's just the first 3 non-zero terms. Then either of these are represented in the power series form with the summation. I believe in the homework, my guess is, I don't quite recall, my guess is they're always going to represent the summation form. So practice those. This one wasn't too bad. I mean, there were these 3 aspects, but each one I think we could all kind of guess our way to getting them after we've seen an example. Other ones though going to be quite challenging, so that's why I will specify on a test. If it's very, very challenging to get to here, then I might just say, yeah, just leave it as the first 3 non-zero terms. Okay, let's stop this video here. Another example in the next one.